Continuing with Chapter 15 on impulse momentum, just to remind you, last time what we looked at was how impulse and momentum are related. That is, if we have an object that begins with an initial momentum, and then there is an impulse, which is a force exerted over time that acts on that original object, it will then change its momentum and have a final momentum given by the sum of these two factors. When we looked at a system of particles where the impulse-momentum relationship could be written as the sum of the initial momenta plus the sum of all the external forces, or the impulses related to those external forces, would be equal to the sum of the final momenta. In the cases where we don't have any external forces, what we found was that the initial momentum was equal to the final momentum. This is what we call the conservation of linear momentum, or just the conservation of momentum for short. And this is something that governs what we usually use this concept when we're talking about collisions. Before we get into collisions, we want to investigate something called the coefficient of restitution, which is something that we touched upon in general physics. For instance, if you take a tennis ball and you let it drop to the ground, you know that it'll bounce. However, it won't bounce as high as it is the original bounce. Each successive bounce will be a little bit lower. This is related to what we call the coefficient of restitution of the ball. It has to do with how does the ball deform as it hits the ground, and then how much of that energy can be regained as it leaves the ground to go back up to a new height. So let's think about how we find the coefficient of restitution. First of all, let's just classify some of our collisions, or what are some of the characteristics of the collisions, and also what are the two types. So in an impact or a collision, what's happening is it happens over a very short time period, but the force of interaction is quite large. We like to define the line of impact is a line that goes through the mass centers of the objects that are interacting, and then it is assumed that the forces are acting along that line. In these situations, we can have two types of impact, a central impact and an oblique impact. In a central impact, basically the motion of the particles is along the same line and also along the line of impact. We would actually call this a one-dimensional collision if we were in general physics. An oblique impact is more like a two-dimensional collision, where the line of impact, and this is the line along which the forces are acting, the forces of interaction, but when the objects came to each other, they were moving at angles to each other. They weren't moving along the same line. And so it is expected that they will go off at angles afterwards. Of course, that's why it's two-dimensional. So we're going to just look at the idea of a central impact and the coefficient of restitution. So in the central impact, the two objects are traveling along the same line, and this is also going to be the line along which the impact will take place. It will also be the line along which the forces will be acting. And so what we're going to talk about in general is sort of as they hit, first we'll have sort of before they collide. Then we're going to have the period of deformation. Then we're going to have the maximum deformation. And so, in a sense, during the deformation, the objects are going from their initial velocities to the velocity that when they move together. And we'll see this later in a picture. The maximum deformation is they have the same velocity because the two objects they no longer have any relative motion, they're moving together, they're deformed as much as they can. Then after that, we have the restitution impulse. And this is where they go to their final velocities. So we're going to look at these steps, and from that we're going to derive the coefficient of restitution. First of all, we're just going to make things a little bit simpler. We're going to assume that our two objects are moving in the same direction. However, one object is moving faster than the other. So object A is moving faster than B, so it's going to catch up to B and run into it. This is how fast they're going before there's any sort of impact. Now, when they impact, there's going to be some sort of deformation. What's going to happen is both mass A and mass B are going to exert an equal and opposite force on each other. That equal and opposite force will be responsible for an impulse. You see the impulse listed for each object. If we wanted to look at the impulse-momentum relationship for this, it would look for, we're going to just sort of focus on mass A for these. So mass A had its initial velocity and its initial momentum. It experiences an impulse from object B, and so that's a negative impulse because the force is to the left that B is exerting on A. And then this is equal to mass A. And this whole deformation impulse will occur until the two objects have their maximum deformation and move with the same speed, which is this V. This is the picture showing when they have their maximum deformation and are moving both with the same speed. Now, after that is the restitution stage. And in the restitution stage, the objects are exerting forces on each other still, but it's sort of bringing them back to their normal shape. And so for A, it was initially moving with that velocity that they had during the maximum deformation. Then there's the restitution impulse, and in the end, it moves with its final velocity. And so that's its final momentum. And then once they've lost contact, they just move on with their final velocities, and that's what the picture looks like. So trying to put this all together, there's basically, when we're trying to talk about this kind of situation, one of the things that we could use in terms of trying to find other values, like let's say that we know the initial velocities of both objects, but we don't know their final velocities. One of the things that we can use is the conservation of momentum. But obviously, we need one more equation because that's how algebra works. That's going to come from the coefficient of restitution. That is going to give us a relationship between the velocities. Let's look at what the coefficient of restitution is. The coefficient of restitution, by definition, is the ratio of the restitution impulse to the impact impulse. For object A, it would be given by V minus VA2 over VA1 minus V. For object B, which I know we hadn't looked at, but it's okay. You could do that on your own if you're really motivated. Now, if we put those together, if we solve that to get rid of the V, we could express the coefficient of restitution as basically the ratio of the relative velocities after the collision, to the relative velocities before the collision. And that's what the coefficient of restitution is. This actually gives us another way to relate all the velocities. It would give us a second equation and would allow us to solve for the final velocities in a two-dimensional collision if we knew the two initial velocities of the object. Now, something interesting is, what does the value of the coefficient of restitution mean? For example, if it's equal to 1, we have a perfectly elastic collision, which, from what you know, might mean to you a conservation of kinetic energy. We talked about elastic collisions in general physics, and that's exactly what it means. It actually turns out that if you assume the kinetic energy is conserved in the collision, that you would find a coefficient of restitution of 1. This isn't really a realistic situation, but something we can approximate it. Another situation, sort of the opposite of an elastic, is a plastic impact, or as we used to call it in general physics, a perfectly inelastic collision. In this case, the two objects will sit together after the collision, therefore there's no relative separation velocity, so the numerator of the coefficient of restitution is 0. And so that, in that case, when E is 0, you have a perfectly inelastic collision. In real life, coefficients of restitution are somewhere between 0 and 1, and here are some values just sort of for reference. As we alluded to, the coefficient of restitution implies that in most cases the kinetic energy of the system is not conserved, which means that energy is lost. The way that energy can be lost is usually through some sort of change in temperature, such as with thermal losses. It can also be lost due to the deformation or the production of sound. We can use the coefficient of restitution in a two-dimensional collision as long as we align one of the axes along the line of impact. This means, again, that the only forces are going to be acting along that line, and so we could say along that axis we could use the coefficient of restitution. That means that honestly we would only be relating in the coefficient of restitution the x components of the velocities. And so this is what our two equations might look like if we were trying to solve some problems for the oblique collision. Here you have conservation of momentum in the x direction. Here you have the coefficient of restitution, which is using the x velocities because of the fact that that's along the line of impact. And finally, it turns out that in these cases, the momentum of each particle is conserved in the direction perpendicular to the line of impact. So that means that the y momentum of each individual particle is conserved. And I want you to think about why that might be true. Go back and think about the law of impulse and momentum and think about why this is true in this case. And that's it for this section.